Yes. Well, thank you all for attending, but the special thanks goes to Saday, a long-term colleague and friend, and working in very interesting fields, now machine learning, like many other people. So I'm super looking forward to your talk, Saday. I'm glad that you could make it, and I'll give the word to Nikolai to introduce you formally.
Okay, thank you, Torsten. And again, thank you, Saday, for coming. Saday is a professor in the School of Computing at the University of Utah, and he also has a joint appointment at Pacific Northwest National Laboratory, both in the US. He was formerly a longtime professor at the Ohio State University and is also an IEEE Fellow, among many other recognitions. His research broadly centers on compilers and high-performance computing, including data movement complexity, which I think we'll hear about now. So take it away, Saday. Thank you.
Thank you very much, Nikolai and Torsten, for inviting me to speak in this amazing seminar series. It's just an amazing set of talks that this is a great service to the community. Thank you. Is my voice being heard clearly enough?
Yeah, I think so.
Okay, so what I'd like to talk about today is some recent work we've been doing on optimizing data movement for convolutional neural networks. The work's primary author is Ray Lee, a PhD student who's just about to graduate. And Yufan Zhu is also another PhD student at the University of Utah, and collaborators Nasco Ronte from Ohio State, Arvind Sukumar and Rajam from Washington State University. I'd like to acknowledge support from the National Science Foundation for this work. So just a second. Okay, so let's start with looking at a simplified version of the CNN computation, where we have three tensors, two input tensors, an input and a kernel. We have the indexes, n refers to the batch index, output channel k, height and width of the image. And this is a summation over input channels and the stencil or extent RNS. That's the kernel is indexed by the input and output channels, and the stencil index is RNS, and input is indexed by the batch index input channel. And we have the H plus R and W plus S indexes. Here I'm ignoring the stride and dilation parameters for simplicity, but the approach is not restricted to any specialized forms. So this computation can just be directly translated into a set of loops, but if we were to just compile and execute this, performance is going to be quite far below machine peak because of the excessive amount of data movement that will be required if we just try to implement this in this form. So tiling is a key loop transformation to reduce data movement in codes such as this. So the key challenge though is how should we find the optimal tiling for a computation like this? So first, in terms of even before we start tiling, we have many possible orders. All possible permutations of this loop are going to be valid. Once we do tiling, we're going to increase the number of loops. So if we just do one level of tiling, then we'll have 7 tiling loops, and then we will have 7 point loops, so that we have a 14-dimensional loop. Now, if we have 4 levels of tiling for registers L1, L2, L3 in memory, then the number of loops is just explodes. So just to show two levels of tiling, we see the point loops at the bottom, and then we have two levels of tiling. Now in practice, efficient codes for CNN are not going to have essentially 7 tiling loops at each level to come up with some 28 tiling loops. So finally, efficient implementations will only have maybe less than 10 tiling loops in any situation. But a priori, we don't know. So essentially, most of them will get degenerate in the optimal solutions. And the actual explicit number of loops will only be a handful. But we don't a priori know which ones they should be and what should be the tile sizes. So if we just look at what is the design space over which we want to find an optimized solution, where many of the tile sizes will essentially become 1 at the end. The design space, however, is explosively large when we consider that there are 7 factorial permutations at each of the tiling loops level, at each of the levels of tiling, and there are essentially 7 tile size variables at each level. So this is the key challenge: an enormous space of tile sizes and loop permutations. So with L levels of in the memory hierarchy, we basically have 7 factorial to the L permutations of the tiling loops to choose amongst, and each of the permutations will include 7 times. Essentially, for a given permutation of the set of loops, we have 7 times L tile size variables. So what are the current alternatives in terms of optimizing CNNs? We have vendor libraries that have been meticulously optimized by armies of engineers at Intel. For example, MKL's 1DNN is a highly optimized library. Then we have systems like AutoTVM that use fundamentally, they have a schema that's provided with a set of tunable parameters, which can be tile sizes, also possibly some permutations. And there is an auto-tuning search process that generates a large number of versions, actually executes them on the target platform, and then identifies the best amongst those. Now, CNNs are purely affine computational structures, and therefore they are in the domain of what polyhedral compilers can do. However, we did some experimental evaluation on a couple of CNN stages from 2 of these pipelines, ResNet 18 and YOLO 9000. What we find, and we'll show results some later, 1DNN is, for most of these stages, 1DNN was the fastest amongst these. AutoTVM is occasionally the fastest, but in general, 1DNN is faster. And anything produced by any polyhedral compiler, such as Poly, PPCG, Pluto, etc., is basically consistently worse than both AutoTVM or 1DNN in terms of the achieved performance on multi-core processors. So why is this the case? What is the challenge really here for polyhedral compilers? Now, on the one hand, polyhedral compilers have extremely powerful loop transformation capabilities for affine computations, and that they represent the state of the art with respect to loop transformation capabilities. But unfortunately, that is not enough in terms of delivering really high performance. And a fundamental problem with the current state of the art in general with polyhedral compilers is that they internally use linear functions that are optimized, linear performance models. And so these are restricted essentially to optimizing linear cost functions to perform loop transformations. And optimizing over tile permutations and tile sizes is essentially fundamentally a nonlinear optimization problem. And therefore, this is a challenge. So the polyhedral compilers are currently essentially only able to do a restricted search. So in fact, even it has to be a decoupled solution for optimizing for tile permutations and tile sizes, currently it can only do an iterative decoupled optimization. So fixed tile sizes and optimal tile loop permutation, change tile sizes and repeat, etc. So essentially we have coming back to optimizing CNNs between these three types of approaches: vendor libraries, auto-tuning approaches, or polyhedral compiler optimization. All of these essentially either search a limited design space, or they use very simple models where maybe the whole design space is open to the optimization, but the fact that the cost models are extremely simple doesn't allow the systems to find really good solutions. So what we show is that actually comprehensive exploration of the full design space of tile permutations and tile sizes using an effective cost model is feasible. So details of this work were presented at ASPLOS earlier this year. So what I will do is to sketch at a high level the main ideas behind the approach to doing this. So here's the high level idea. So we have a design space that's extremely large. It's the product of the number of possible tile loop permutations cross product with all possible tile sizes for a given tile permutation. The overall approach that we take in terms of trying to overcome this design space explosion is as far as loop permutation choices is concerned, we use an analytical modeling strategy to prune away a huge number of the possible permutations by showing that a small subset will have provably less or equal data movement, or contrarily, a large majority of the cases can be pruned away because they can be provably shown to have higher or equal data movement than the ones that we retain. For the tile size optimization, we will formulate and solve a constrained nonlinear optimization problem that can be solved for specific CNN problem sizes and architectural parameters of the target multicore system by off-the-shelf solver. In this work, we used IPOPT, but there are other solvers that could be used. So here is a very high-level overview of the three-stage process for the optimization. First stage is that of modeling and pruning. Analytical cost model for data movement volume as a function of tile sizes is developed. And then analytical pruning is used to restrict significantly the number of explicit tile loop permutations that need to be considered. And so what we show is that of the 7 factorial, which is about 5,040 possible permutations, we can actually prune it down to 8. So now each of these will have specific parametric symbolic expressions for cost. And so generate cost expressions, which for a particular CNN convolution specification can be solved using the nonlinear solver to find the optimal tile sizes. And so then we could either just, the last stage is that, so concrete code is generated by using a microkernel that is a Bliss-like microkernel for CNNs, surrounded by these tile loops for whose permutation and the tile sizes have been solved. We could either just take the modeled best, or we could choose to execute a few of the top choices. And so that's the overall overview of the process of optimization. So now I want to use matrix multiplication to just walk through the main idea for the symbolic expression generation for modeling. So let's imagine that we have a one-level tiling of matrix multiplication as shown here. We have the point loops within a tile are shown in the in the highlighted box. So those are point loops Pi, Pj, Pk going over tile extent Ti, Tj, Tk. So the problem sizes are Ni, Nj, Nk, and we assume that these are much larger than the cache capacity. And we're going to choose some parametric tile sizes Ti, Tj, Tk for the 3 dimensions that. And we assume here that these are large enough that we are not going to waste cache capacity. And so this is an assumption that's needed so that we can facilitate the modeling of the symbolic cost expressions. So you start with one tile. So the point loops here, the statement is accessing data which is indexed at the starting tile point, and to which we add the point index. So we have the footprints of the tiles for A, B, and C are highlighted as A tile, B tile, and C tile. So this is, so each of these, so the A tile will be of size Ti times Tk, the B tile will be Tk times Tj, and C tile will be Ti times Tj. So now to start with, then we can say that the data volume just for executing one tile, assuming everything starts off in memory, will simply be the sum of the footprints of the tiles. So there will be Ti, Tj plus Ti, Tk plus Tj, Tk. Next, as we step through the innermost tiling loop, Tk, what will happen is, since Tk index, the K loop is indexing A and B, but not C. So we'll see that we will move to adjacent disjoint tile footprints for A and B, but C will retain exactly the same tile footprint. So what we can do is to simply compute the total volume for data movement for all iterations of Tk by simply translating from, so we see that wherever we have Tk in the expression for at the lower level, that has extended out to Nk because we step through the in steps of Tk for the whole problem extent Nk. But for the first, for the array C, which did not have a change in the footprint, the sub expression stays the same. In the same fashion, we can essentially step through each of the loops. So when we step through the J loop, J is explicitly present in B, and it's explicitly present in C, but it's not explicitly present in A. However, assuming that we had chosen reasonably large tile sizes so that we didn't waste cache capacity, as we run through all of the A tiles to run through the full problem extent Nk and reset and start again, we will need to reload all of the data for A, because it won't any longer be in cache. So we can essentially generate the total volume expressions. So again, we have for C, it goes from Tj to Nj, and similarly here we will have this go from Tj to Nj. Now for A, the volume which previously was Ti times Nk, we are going to have it be reloaded each time for the J loop. So we have a multiplier Nj divided by Tj. And so in this fashion, now we do one more step. We run through the I loop. Now we will have different tiles in I, different tiles in C. For B, we will repeat the whole thing, but we wouldn't have it in cache. So we have to have a multiplier that corresponds to Ni by Ti. So this gives us at the end, so this is the expression for data volume for execution of this for matrix multiply for this particular tile loop order Ti, Tj, Tk. Now for each of the possible tile loop orders, we can do the same kind of inner to outer traversal of the loop nest to generate a suitable symbolic expression of the problem sizes and the tile sizes for the total data volume as a function of these parametric tile sizes. So next, we consider how we do pruning. So now I've shown here. So the same kind of process is explained in the Ask Class paper, where we can do the same kind of modeling for the CNN computation, just as I showed for the simpler matrix multiplication computation. So for a particular permutation shown here, the volume expression turns out to be what is shown below. It is parametric in the problem sizes n and the tile sizes t. If you change the permutation so that, so let's say we consider this. So that's another permutation where a couple of the tile loops are permuted. The volume expression is shown below. Now, if you compare these two volume expressions, you will see that these two terms are identical. These two terms again are also identical. So of the three summed terms, the one that differs is the one that is highlighted now. But if we focus on this, we see that it differs because of some subterms, and we can show through a simple identity that one of them is always going to be less than equal to the other. And therefore, this is the fundamental basis for pruning away a large number of these cases. It turns out that that out of the 5,040 possible 7 factorial permutations, you derive the expression for each one of them. It turns out that the vast majority of them can essentially be pruned away. So in this particular example, we can conclude that one of these loop orders can never be better than the other one, and therefore we will never need to consider. So essentially, out of the 5,040 possible permutations of the 7D loop nest for CNN, we can show that there are only 8 equivalence classes of permutations that dominate all the other 7 factorial, where domination means that they are going to have volume expressions that are probably less than equal to the corresponding volume expressions for the other ones. And so these are listed in outer to inner loop order, and what this a set of them in curly braces means that permutations within those don't change the cost at all. So essentially, amongst these 8 equivalence classes, we can just need to evaluate one of them, because all of them from the cost point of view for data volume are going to be identical. Okay, so now let's look at what happens when we want to model a multi-level cache. So first, let's look at tile size optimization problem for a 1-level cache. So for a 1-level cache, the optimization problem is find X that minimizes this function for the data volume expression such that the footprint is less than the cache capacity. Now, if you want to extend to a multi-level cache, we need to minimize the estimated data movement. What we do is to minimize the estimated data movement time for the most constraining cache level, because we assume that data movement can happen concurrently between the different levels. And so let's assume that the estimated data volumes at 3 different levels, these are all symbolic parametric expressions of tile sizes, dv1, dv2, and dv3. So what we do is to scale dv1 by the bandwidth 1, dv2 by bandwidth 2, and dv3 by bandwidth 3, which are known parameters for the architecture. And what we need, so essentially each of these FIs is essentially a lower bound on the amount of time it will take to move that volume of data through that level in the cache hierarchy. And our objective is to minimize the maximum amongst F1, F2, F3. So we want to find the set of multi-level tile sizes such that we minimize this maximum function. So the way that we do this is by actually solving 3 optimization problems. So figure on the right is essentially illustrating, assuming we have a one-dimensional function set of functions f1 and f2 and f3. So essentially what we want is to find here the minimum of the maxima of these three functions. So we can see that we can divide the full index space into regions where a particular function is the maximum. So for example, here, the region A marks the part of the total space where f1 happens to be the maximum. Similarly, we can mark regions f2 and f3. Now, when we want to do this optimization, obviously we don't know the form of these functions explicitly, but what we do is to essentially solve one optimization problem for region A by simply adding a constraint in the formulation of the nonlinear optimization problem, saying f1 has to be greater than or equal to f2 and f1 should be greater than or equal to f3. So in which case, that essentially defines region A in this figure. So we solve each of these and then take the one that is the best solution among these, and that's the approach we take to solving the min-max problem. Okay, so let go over some experimental evaluation of the code. So essentially, we solve the multi-level optimization problem, and then we generate code by using standard GCC or ICC for the particular loop permutation and tile sizes that have been designed for a particular CNN. And we compare with 1DNN and auto TVM. So we for that we run auto TVM using their suggested script for 1,000 iterations to find what the best solution that it finds. And in the next slide, I'll show a comparison. And as far as our optimization, I showed two mopt1 and mopt5. So mopt1 is the performance achieved by the best predicted configuration per the model. And mopt5, we take the 5 best solutions produced by the model and run all of those. So here is the performance results on I can't recall whether this was an 8-core. We have results for an 8-core system and an 18-core system in the paper. So this is one of them. The mopt1 is marked in red. mopt5 is in yellow. The baseline is TVM. So the line 1.0. So all of these are speed up relative to the that achieved by the best found by TVM, by auto TVM. Then the blue bars show 1DNN. So what we see is that in general, mopt1, that's the best configuration chosen, is close to mopt5, but there clearly are a number of exceptions. And the reason for this is that the modeling approach that we implemented is only models directly the data movement volume, and then we have a slightly ad hoc way of enforcing some tile sizes for the parallel execution. We tried to add some additional constraints so that we have enough L2 level tiles within an L3 level tile to support the amount of concurrency needed for the multi-core system. So as a result, the parallel, there are some cases where that doesn't work out that well. So in those cases, it turns out that one of the other choices that was produced for the data locality optimization has a better fit and load balancing with respect to the multi-core case. So I'm showing here results for the multi-core execution For sequential execution, we don't see much deviation between MOP1 and MOP5, but for the multi-core case, in a few cases, there is a deviation. Now, in terms of comparison against auto TVM, you can see that both MOP1 and MOP5 in general are performing somewhat better than auto TVM, although clearly there are cases where we are actually underperforming too. So there are some cases where at least MOP1 is underperforming. As far as there are a couple of cases where even with MOP5 we are slightly worse than auto TVM, but most of the cases you can see it's basically above that line, 1.0 line. And with respect to 1DNN, I would say that the performance achieved through MOP is generally comparable or better than 1DNN. So here's a slide that shows some of the results from our attempt at validating. We sought to validate the model to see, how effective is the model with respect to actual execution. So here in this experiment, we generated a set of 100 tiled configurations. For each tiled configuration, our model will predict some metric, which is that min-max cost with respect to the different levels in the memory hierarchy. And we compared the runtime's actual execution for the model predicted best versus the actual best among all these 100 configurations in this experiment. And we are showing the percentage loss of performance, which is essentially comparing the runtime of the model best with the runtime of the actual best. And if both are equal, then loss of performance is 0. But if the model best is not quite as fast as the actual best, then we have a loss of performance. So you can see that in general, the loss of performance is under 5%. In many cases is under 3%. So the modeling approach seems to be quite effective. Okay, so that's the first part of the talk was on the question of how do we perform a comprehensive design space exploration for CNN, and the target here was multi-core processors, multi-level cache, essentially a shared memory framework. So next part of the talk, I want to discuss what about doing the same kind of optimization, but now we have a distributed system where we have processors with local memories. So here clearly we have a larger design space than shared memory optimization, because now we need to consider the placement of data. All of the data for the problem has to fit within the collective memories of the distributed system, and we need to consider communication schedules. Now, it turns out, though, that the structure of array indexing patterns in CNN enables a two-step optimization approach that I will sketch. First is to formulate and solve a two-level global memory parallel tile optimization problem, very similar to what we solved for the multi-core case, and then do a translation of the global memory solution to a distributed memory solution. So I'll use again matrix multiplication to explain the high-level idea. So we modeled the global memory optimization problem as a two-level tiling problem, where at the outer level of tiling, we're going to partition the iteration space. This is the full problem iteration space into P equal work partition. So this is what we'll call a work tile or a work partition of some parametric size Wi, Wj, Wk that are yet to be determined, and one per processor. And then there is an inner level of tiling where each of these work partition tiles is going to be executed as a sequence of memory constrained tiles of parametric tile size Ti, Tj, Tk. So, so what we see here on in this picture in blue is the full iteration space of the problem, which is basically parameters Ni, Nj, and K. And so we are dividing that into a set of work partitions shown in green that is going to be executed by one processor. At this point, the shape of this tile, the work partition of a processor, is parametric. We are going to allow for all possible values. And then inside the green box, we see the orange. That's the tiling of the iteration space within a single processor. So the constraints will be that the orange box, that tile, should be able to be executed in the available memory of the processor. So the data footprint of a tile must fit in local memory. So the optimization problem is find the values for the parameters W and T, where W is Wi, Wj, Wk in the case of matrix multiply, and Ti, Tj, Tk, to minimize communication costs from global memory to each processor. So all the processors are going to proceed concurrently with respect to their execution. And here the abstract model is that we can do a read, modify, write onto the global memory. So there's no, in this model, there's no communication between processors. Everything goes in and out from a virtual global memory. So let me go over how this global memory optimization can be done using matrix multiplication as the example. So here we show a 3D iteration space for matrix multiply, where we have extracted just the subtile or the work partition that a particular processor is going to execute. It has sizes Wi, Wj, Wk, and then we're going to use tiles of size Ti, Tj, Tk. So now for a particular tile loop order for this processor, so here we don't consider, there's no issue with respect to the different processors. They're all going to execute concurrently. To execute their W partition, but now each processor is stepping through its tiles over its work partition range in steps of its tile size. So here we can formulate this in a similar fashion to how we formulated the data volume cost movement, because it's again between, it's essentially a one-level memory hierarchy. This is the kind of expression which will be very similar to what I showed for the matrix multiply, where the W's are essentially the equivalent of the problem extent, because that's the subset of the iteration space that this processor is going to execute. So we have a constraint optimization problem where this function Wi, Wj plus Wi, Wj, Wk into 1 over Ti plus 1 over Tj. So this is really, as a function of the tile sizes, the cost for a particular processor in terms of total volume of data movement from the global memory. So the constraints are, one is that the Wi, Wj, Wk product should be equally dividing the full iteration space Ni, Nj, and K. And then this second constraint is the memory constraint. Each processor has only M total memory, so the sum of the footprints of any tile T has to fit within that memory. So the solution for this can actually, so for specific problem sizes, we could try to solve this like we did for the ASPLOS paper for multicore optimization. But it turns out that we could actually solve this more generally analytically using Lagrange multipliers and the Karish-Kuhn-Tucker optimality conditions. So I'll explain that for matrix multiply. So here we have, this is the cost function from the previous slide that we want to minimize. And now as a first step, we could essentially eliminate one of the variables from the optimization problem by realizing that Tk, which only appears in the constraint for the memory constraint, does not appear at all in the cost function to be minimized. Therefore, we can conclude that since it constrains the values of Ti and Tj, which we want to try to maximize to minimize this function, so we should set Tk equal to 1. So now we have reduced from 6 variables to 5 variables. Then another observation that's key to the analytical solution is that we can easily reason that any optimal solution to this cost function must satisfy one of these two conditions. Either we must have that Wk the tile size along K should be equal to the problem extent Nk, or it must be the case that the local and work partition sizes Ti and Tj must be equal to Wi and Wj respectively. So the reasoning behind this is that supposing we consider Wk is less than Nk, then we can notice that this term is the same as this term. Essentially, that's a constant. Wi, Wj, Wk is forced because of the load balancing constraint. And therefore, we can increase Wk and decrease Wi. So essentially, we can simultaneously increase Wi and Wj and decrease Wk to keep the second term fixed. And in this, sorry, the other way around, we can decrease W and Wj and increase Wk simultaneously to decrease the cost function if we have Wk less than Nk. Now, the only condition under which we won't be able to do this is when the W and Wj have essentially can't be lowered any further because they have hit the Ti and Tj. So that's the work partition size has to be obviously larger than the tile size chosen. So this allows then to reason with respect to these two separate cases. And I'll just sketch how for one of the cases where we have Wi equal to Ti and Wj equal to Tj, how we can solve it. So under this condition, we can convert the system that we had on the previous slide to this. And in fact, I should also set this Tk as being set to 1. So now you see that we, because of the load balancing constraint, that is W at Wj, Wk is Ni and J and K by P. So we essentially have reduced the system to one that essentially now has only these two variables, Ti and Tj, over which we have to do the optimization. And this can be simply solved by setting up the KKT Tucker conditions, forming the gradient with respect to L, setting that to 0, and we will get for the lambda has to be greater than or equal to 0. Each of those gives a different solution. So in fact, these turn out to be exactly the same as what is well known for the 2.5D and 3D algorithms for matrix multiplication. So the other case, Wk equal to Nk, can also be similarly solved. So essentially, for a particular permutation, the solution is what is shown here. And then if you consider all possible tile permutations, we get the condition and the cost as in this fashion. And this really corresponds to what in the literature is known as the 2D algorithm, the 3D algorithm, and the 2.5D algorithm for matrix multiplication. So let me then go to the next step, which is so far we have basically solved an abstract global memory optimization problem. Now, how does this relate to an actual distributed memory algorithm? The construction is based on essentially the observation that the nature of the solution that we produce, the access patterns are such that processors that the tiles that are adjacent along the I direction turn out in identical steps to access exactly the same slices of the B array. Similarly, as far as the A array is concerned, along the J dimension, adjacent tiles that are along, or all the tiles essentially along J have exactly the same footprint on A, and they need to access it at exactly the same time. So from the global memory solution, we can essentially directly construct a distributed memory solution where we replicate the output C array along the k dimension, along the third dimension. And for the other two, we distribute the slices of the array. So for example, B in this case, if there are two processors and two work partitions along I, we just have it divided amongst them, and where in the global memory solution, they would identically retrieve slices from the virtual global memory. Now we have the holder of that slice just do a broadcast along one processor dimension. So essentially, that's the main idea behind the way that we can convert the global memory solution to a distributed memory solution. So the same approach works for CNNs in general in terms of the conversion. However, the expressions that we obtain for CNNs using the same methodology that I described are too complex to completely solve analytically. So what can be done though here is to transform the problem to another one, which is a relaxation of the original problem, but one that structure is such that we can use the same strategy as for matrix multiplication to solve analytically. So essentially, it involves simplifying these kinds of terms that occur in the CNN's formulation of the constraint optimization problem to get rid of those. And so essentially, we are solving a modified problem where we use a modified memory parameter. And so we can find the optimal solution to the transformed problem. And however, that solution, because it's a relaxed version of the actual problem that we want to optimize, is not going to be a valid solution to the original, the actual cost expressions for CNN. However, importantly, there are two properties here. One is that it serves as a lower bound to the best possible achievable cost function for the actual function. And secondly, it acts as an up. If there is, we can prove that there is, we can do an upper bounding with respect to the actual problem by identifying and by constructing a difference amount delta with respect to the memory, that such that if we solve the modified problem with a smaller amount of memory, then the tile sizes obtained from the modified problem will actually satisfy the memory requirements to solve the original problem. So essentially, that's kind of sketched at the bottom here. The blue ring indicates the problem, the solution to the relaxed problem, and then it serves as an upper bound so that we can now shift it from the solution with actual memory M to something that is solved for an amount that subtracts this delta from the actual amount of memory available in the physical system. That solution, even though it can't be guaranteed to be optimal with respect to communication volume, it turns out to be a really efficient solution for the CNN problem. So this is the final summary solution for the CNN, for an efficient distributed algorithm for CNN. And as with the matrix multiplication analogy, we do have the similar conditions, and we have the equivalent of the 2D, the 3D, and the 2.5D variants for distributed CNN, with these being the conditions under which those can be implemented. So the details for this are in a brief announcement that was presented at SPA earlier this year. So let me wrap up. So main takeaway is that even though the design space of possible tile permutations and tile sizes for CNN is enormous, however, model-based explorations of for data movement optimization is feasible. So really interesting question and a direction for ongoing research is how can performance models for optimizing loop transformations, especially tiling in compilers like polyhedral compilers, be improved using ideas that have been developed with at this point manually for the CNN computation. So ongoing work includes generalizing this approach. So the approach that I described, the inner to outer development of symbolic expressions for data volume, is not really restricted to matrix multiply or to CNNs. It can be generalized and automated for a larger class of tensor computations, including tensor contractions, things like MTT, KRP, and others. And the other direction of extension here is to try to apply this kind of methodology for co-design of accelerator parameters. How much memory should you have? How many registers? How many? Given some total energy or space constraints on a chip, what among the space of possible CNN design parameters? How can you co-design it to optimize it for a collection of CNN stages that are of interest to execute on that accelerator? Okay, so I'd be happy to take questions at this point. Thank you.